So our next speaker is Edwin Peters. He received his PhD from the University of Newcastle, Australia. He is currently employed as a research associate at the University of New South Wales, Canberra, where he pursues his interests in signal processing, satellite communications, RF systems, and space situational awareness.
Thanks for the introduction, David. So I'm presenting some joint work I've been doing with some of my colleagues on combining optical and radio frequency measurements for SSA purposes. So quickly introduce the problem, then show some of the hardware that we have around, show some of the initial data processing results that we obtained, and basically give a brief summary. So jumping straight into it, it's quite crowded around Earth. It's orbit, around 27,000 objects are tracked currently. And most of these are larger than 10 centimeters. Limit mostly is because it's very hard to track stuff smaller than 10 centimeters because of radar cross sections. So out of these 27,000 objects, a bit over 4,800 are operational satellites, with the far majority of them being in low Earth orbit, and that especially accelerated the last decade with a lot of commercial players putting constellations up. And actually in the next 4 years, this number is expected to double, so we'll have over 9,000 satellites in orbit. Currently, the position of these satellites is mostly, or the orbits are mostly provided by the 18th Space Command in the form of two line element sets, TLEs. They also issue conjunction data messages, so-called CDMs, if some satellites are getting close to each other or to other debris objects. And currently, these messages are issued roughly when there's a chance greater than 1 in 10,000 to collide, or to collide with something in LEO, and in geostationary orbits they look at the missed distance being smaller than 5 kilometers. So considering how small the objects are, even geostationary compared to those distances, there's quite a lot of uncertainty. So with all these new objects coming up, there's an increasing need for object detection early after launch, because actually if something is launched, it often takes a while before you can get an accurate enough orbit to start communicating. Also, if non-cooperative partners put stuff in space, you want to find it as quickly as possible. Also, high precision orbit refinement becomes more and more important, especially with using narrow beam, high gain RF equipment or even optical communications. You need to know where to point your equipment at. Maneuver detection is another really interesting field to start looking into, especially since propulsion becomes available on smaller spacecraft. And TLEs actually don't capture that very well. Space health detection, which Melrose mentioned a bit earlier as well, is an interesting thing to look into, especially if two objects, for example, are on conjunction course. If one shows signs of deteriorating health, it might be fair to assume that that's not the one that's going to move out of the way. So this is where the government-funded CSVP project comes in place, which is titled A Sensor Network for Integrated Space Traffic Management for Australia, which we work on with our collaborators, all Australian-based Clearbox Systems, Blue Ridge, and Capricorn Space. So we look at using observations, RF, so radio frequency passive observations, combine this with data obtained from optical telescopes, and use this for orbit determination, orbit refinement, maneuver and anomaly detection. And the focus is to build a low-cost system that will cover Australia, maybe even outside of Australia in the future. So I'll show some of the hardware we have at the moment. So this is our SAT-HOT site on the top of the UNSW Canberra building. It's a couple of kilometers away from here. And this site features RF sensors, where on the left-hand picture you can see two antennas. These are omnidirectional, so they can generally scan the whole horizon and pick up everything there, including interference. The one on the right in the picture, it's a bit hard to spot, I think, on the slide, but that's an interesting antenna because it covers all the way from the VHF band up to the mid-L band. So you can capture a lot of information with that. In the middle picture, there is a rotator with a KU band dish, so you can use that to track, for example, just some geostationary television stations. And other satellites. There's an S-band dish coming up there as well. And on the right-hand side is a directional antenna, so these operate in the UHF band, so they feature a lot higher gain, higher interference rejection than those omnidirectionals. So current RF capabilities are covered by our UNSW side and 2 sites by our collaborator Clearbox Systems, one in Adelaide and one also in Canberra down in Fishwick. And they cover VHF, UHF, L-band, S-band, and KU-band. At the moment, these bands provide us enough data for the current purposes, but more bands can be installed. So just an example, what would data look like that we captured with this? So this data we captured last week is an Indian LEO CubeSat called Saral that's transmitting in the UHF band. And on the left-hand side, that is a so-called waterfall plot with time on the horizontal axis. I think it's a bit hard to read. Frequency on the vertical axis. And the color intensity tells you how powerful the signal is. So the brighter the color, the more powerful it is. So the left-hand picture is captured by the omnidirectional discone antenna. So this antenna did not have to track, it was just pointing up, and we took data in from it. The right-hand side picture is the same path, but recorded by our directional Yagi antenna. So that had to track the satellite, but you can see there's a lot better signal-to-noise ratio. You can actually see the side lobes very clearly. Another really interesting feature that you can see is on the left-hand picture, you can see all those vertical bars that go through, and that's actually local interference from terrestrial emitters most likely. And because our receiving antenna is vertically oriented, it will pick all that up. The receiver antenna on the right-hand side was horizontally oriented, so they'll actually not pick much of that up, so it's a lot less of that interference. So this is just an example of capturing with different methods can provide useful for each idea. Another, on the optical front, we have our Viper wide field of view telescope. It's located in Yas, around 80 kilometers north of where we are. And it's, for being a telescope, quite wide range of view, 1.5 degrees. It has a NVIDIA Jetson, so a little computer on it, so it can do edge processing at spot. And it's going through the final stages of commissioning, so hopefully it should be operational in a few weeks. And on the right is just a beautiful picture it took of the moon a while ago. Also, we have access to the Falcon network, which Melrose presented beautifully earlier, and Steve as well. So I won't spend too much time on that, but it's basically shared between the US Air Force Academy. We have a telescope on site as well, and we use it to capture pictures from satellites. And this is an example data recorded by Steve Geely. Where on the left-hand side you see M2 and A and B, around 30 hours after separation. And on the right-hand side you see the light curve, so that's basically measuring the SNR. On each of those still images, you can actually see both of them are present at the same time at the end of the pass. So, now we have presented a lot of the data that we have, but how are we going to use this? So the idea is that we, on each of the sensor sites, do some edge processing, can measure parameters out of the data, then through some open source protocols can transfer this into the cloud. For example, Amazon Web Services that then aggregates this data. We have an on-site supercomputer with a lot of GPU power that we can do some heavy processing and orbit determination to it. And that provides data to the user in the form of orbit research data to the researchers. There's also a scheduler that we can priority schedule what objects we want to track, and ideally it gets automatic sensor allocation. If we know something very precise where it is, we can put a narrow field of view antenna or a telescope at it. If we don't exactly know where it is, we need wider field of view equipment. An example on some of the processes that we've done so far. So this is on RF data. So from one side, what we can measure is frequency offset, or Doppler. As the object flies over, the frequency goes up as it approaches us and goes down as it goes away from us. So if you map enough of those Doppler curves, you can actually fit an orbit to that. So to the right-hand side is an example of a waterfall. Again, time on the horizontal axis, frequency on the vertical of our M2 pass. And overlaid is a frequency estimation. So the way how this is done, I'm not stepping too much into details with it, but we do a coarse acquisition, where we basically do a search for energy, or actually energy fitting a pattern. And then we do a fine estimation where we detect what the carrier is doing. And the color, like the red dots on that figure, that is actually the coarse acquisition results. And if they are out in nowhere, it's basically just because in that block of data didn't find anything. And the color that goes from blue till, pink, is the fine frequency estimation, where the more blue is the color, the more accurate the frequency estimation is. On the left-hand side in those two figures, can you see the blue lines in there? I hope you can. That is basically that algorithm run on simulated data. We simulate the Doppler curve and then check how good are the estimations compared to what we set the Doppler to. And on the horizontal axis, you can see the SNR level, so signal-to-noise ratio of that signal that we put in. And on the vertical axis, you can see the frequency error, mean and standard def. And actually, you can see, like, of course, higher SNR gives better data. But in the bottom plot, I thresholded basically on covariance matrices based on the fit. So basically qualify that the estimation gives automatically for free. If I hard threshold that, we can even at 4 dB SNR get measurements that are within 0.1 Hertz accurate. By putting a threshold different, we can get useful measurements at lower SNRs as well. So this basically just tells us that the quality indicator is actually good to tell us what measurements are useful, which ones are not. An example of application, M2 when we launched that last year. Normally, if you launch, you get a simulation from the launch provider that you can propagate, and that's basically all you have to track the satellite with. Sometimes the launch gets a bit delayed, which gives you a time shift, and there's some other uncertainties. So it's sometimes a bit hard to fetch a satellite. And what we did here, if you look, so this is actually using our open source tool called STRF, made by a Dutch guy called Kees Basa. The graph that you see, the continuous line, that is the TLE that we predicted based on the launch provider's information of what the Doppler curve would look like. And the dots is what we measured and estimated. You can see there's a little bit of an error. You can do a fit to that, then it fits pretty good. And if we look at that over a couple of passes, so here the left-hand side, it shows the passes. So I look per satellite pass, and see it shows the frequency error observed compared to what a propagation of that TLE would give us. On the right-hand side, also again passes, but it shows the time difference, so how much that curve would have shifted to the left or right in the previous plot. And actually, if you look at the blue line, so that is the TLE generated based on the launch provider's data. You see there's a quite big error. And the interesting line from ourselves is the blue one, not the blue one, the green one, which is where we fitted the TLE onto 4 passes of data. And you can see even after 40 odd passes, which is around a week, 8 days of communication pass, it was actually still pretty accurate. After that, the commercial issued TLEs actually were getting decent enough that we could use them for communications. So just to summarize, currently we have 3 RF sensor sites established. We have the Viper telescope almost running, using the Falcon telescope to capture light curves and information. I've done frequency estimation on RF. I showed one example, but we have to use different methods. We've done orbit refinement. What we really have to get into is doing orbit determination on both optical and RF data combined, ideally using some open source tools like ORCID and GMAT. We want automated tasking of sensors, and also start taking advantage of multiple sites using triangulation methods. That's what I had. Any questions?
Could you just expand on how this application could be used for maneuver detection? So is that just basically detecting changes from what you measure versus your model, or is there other applications for that? Thank you.
Yeah, that's one of the things we're looking into, but yeah, basically the derivation from your model, which will require that you have a very accurate model of the orbit. If you know exactly where it's going, if you then see it does not, you can fairly assume there's a maneuver happening, especially if you observe it over time. You might be lucky and see it happening as it goes over you. For example, in these Doppler curves I showed, the frequency might deviate a bit different. But that's exactly one of the things we want to look into, yeah.